Hello, let's get started. So today I'm gonna make like an extra review on method 25 about like a volume. Alcohol is 2. It's a review on volumes because volume is a hard part of the course. So I'm just gonna make about like a washer method and a shell method. It's a review of volume problems. So the room I'm at right now is ECE 105 because this building is like more safer because I tried like Beckley Hall 131, Johnson Hall 102, Condon Hall 109, Condon Hall 128, and the Condon Hall 110B. Found out this is like the best room because there's no one people like a spiny. And they probably open like 24 hours a day. So I don't even want to be just to kick out of the classrooms and lecture hall. So I'll do an extra review of volumes. So the first type of volume it is 6.2. It is like the washer disk. So it is obtained by rotating the area by horizontal axis. If they're in terms of x. Well, the reason I'm finding like empty lecture hall it is because I have an all document camera, but I don't have a USB adapter. So I could just find some empty lecture hall that I could just stay motivated because I can't like very motivated inside of my apartment. That's one of the purposes. And we always find it's like rotating. So we have a first cases is rotating them by the x-axis. So it's just like a washer problem. So with is case 1, it is rotating about the x-axis. It is like this if you have a 2 functions. But if it's like only one function, treat the next lower curve as a 0. So if you have perhaps one curve, another one curve is like this, you will get something like this. And this is gonna be f of x. This is gx from A to B. Perhaps this is A and this is B. If you rotate them by the x-axis, you will get like so it's like a washer. So what you get is like this kind of a like this solid. If you rotate them about like x-axis, and this is like the solid, like a solid will be obtained because you take like a slice from the cross section, and just rotating the cross section you obtained, and this is like uh so this is like a washer. And the volume it is from B to A, that's pi, is just the area function. So just fx minus gs and pi squared. Fx squared minus gx to the squared, then dx. If it's a one curve, treat the gx as a 0. In case 2, here we can introduce case 2, rotating about any horizontal axis, y equals to c. For this time, it's like a c is above the top curve. So in this case, it would do like this. Perhaps this is the region. And we have this is the axis. We have it as this is the function from A to B. You're rotating about perhaps it's the y equals to c axis. This is a y equals to c. Rotate them as this is how we get like the curves. Well, it's not like a perfect drawing here, but I did my best. So you can see this like this is like a washer. This is like the perhaps this is like the area region. It is f of x. G of x. This is the same area. That is bounded by the curve. And if you take area of the slices, perhaps this. Well, I don't know how to get this. So it's like this. So it's like a washer, right? If you look at it, yes, it's a washer. This time we have an outer radius. It is fx minus. It is c minus fx. It's a c. Gx is so in this so fx gx we have r out. It is c minus gx. Because this is r in. R out, it is c minus fx. So it the volume is e over a pi of r out squared minus r in squared then dx. This is a volume. And then the third case is it is when the curve is under and what we call the x-axis. are these different colors? I'm just been confused by this. It's like the purple. Okay, so still roughly about horizontal axis y equals to z. But this time is it's under. It's like C it is smaller than is G of X. So perhaps that, sorry, I was not on the graph here. Well, too bad. Perhaps this is the area function. This is G of X. This is F of X. A to B. Perhaps you were talking about this axis. Now remember, right? This is y equals to C is under the GX. It's about 1.5 radius is like it's like rotating. This is the washer obtained by rotating the region. See, it's like a washer. There's a balance with like shape here. I take a slice. All what my figure now to scale. So hope you guys appreciate it. I tried my best. So in this case, is R out. It is fx minus c. And inside it is gx minus c here. Just make sure your volume it is not negative. So volume it is b minus a is pi of r out squared minus r in until squared and dx. And let's do like number 5 is like the shell method. Sigma 3 volume by cylindrical shells. So it's rotating the region by the vertical axis. So about the vertical axis. In this case, we will expect a few more like kind of like cases here. So for example, we have, I'm sorry that I'm reusing the same color because I didn't expect what color I just take in. So hope you guys appreciate it. So it's case 1, it just rotating about the y-axis. So like shell. So if you have like a region that is bounded by perhaps this is a region. Also, just they're just bounded by. And this is just rotating about like the y-axis, so we're obtaining like a shell. What the hell are we drawing like a shell? Because like this is like the shell here. You will see like the shell. This is the area. Perhaps this is gonna be f of x. This is gonna be g of x from a to b. This is like the area function here. There's shaded region. And the shell here, you just say it's a shell. This is like the bottom base of the shell. Sorry if I take too much time on just painting this shell, but it's more like visualize it, isn't it? So shell is inside of a shell, right? And it's like the volume, it is gonna be b minus a is 2 pi x. This area volume is fx minus gx. Yep. Fx minus gx dx. In case 2, it is more complicated, but is doable. Let's do like another, just introducing the concept here. I'll get to the example later after this. Rotating about the horizontal axis y equals to c. With x equal to c. Well, it's just like c it is smaller than a. I have this like, and this is like the region. It's like the same region. Sorry, I couldn't just drawing it perfectly because I'm a bit of a nervous when I'm inside of lecture hall recording those videos. So perhaps this is x is equal to c here. Rotating them, it's like the shell. This is like the shell here. This is cylindrical shells. You see here is like a shell, right? It is f of x is g of x. This is the volume of the cylindrical shell. Because we rotate them. And this says we don't have a radius, so like a shell. So we just shade this region, and then we just evaluate this integral to find the volume. And the volume of the shell, it is v equal to b of a is 2 pi is going to be x minus c. X minus c f of x minus gx, this is the area, dx. I'm just coloring the regions. This is like spend too much time on coloring this region. Apologize for it, but it's like basically the same thing, but just changing like the radius, like a 2 pi x instead of a 2 pi x minus c. Like the shell here changes. Then case number 3 is we are rotating about some vertical axis. Well, the y axis is c, but b is smaller than c. Horizontal axis, it's going to be a vertical axis. X is equal to c, but b is smaller or equal to c. So in this cases is it's like this type of shell. I would expect it's like if sorry if I just draw like the same shape of this shell. If here is like y is x equal to c, here is going to be a, here is going to be b, equal to c axis. It's like the radius, inner or outer shell is like a wider shell here. You can see this wider shell. This is like this is like the area section. Color. This whole thing. Well, they're not like a perfect, but I try my best. Yeah, I had to do this. Like you can see, this is a shell here, and the volume is b over a. 2 pi is c minus x fx minus gx dx. And now let's try some examples here. This region A is bounded by fx equal to x gx equal to x squared. This part A is set up the integral of the area of region A. So we can draw like a visual here. I'm just gonna use different colors here. You can draw, if you can visualize that, what is like the region A looks like. You can just draw this picture. Is it looks like this. I'm just gonna assume is this region. Their intersection is like 1, 1, and a 0, 0, top over 0 and 1, y fx is above the gx. So the area is going to be 1 and 0 is x minus x squared dx. And this is area. If you want another part B, it is set up the integral of the volume of the solid obtained by rotating the region about the x-axis so it's the same region, but we have x-axis and the y-axis. So that be like different. We have an outer radius and inner radius. So the outer radius, it is gx, so it's like the same thing. So because we just had this have this region here, it is they're not to scale, but I tried my best. Three, it's probably like this. Well, they're not the best. They're not best washer, but it's a purple washer. And this is the x-axis. This is like the sketch of the region. And this is like the area. Perhaps you take a slice, it is just this slice out of it. And it's a washer, right? And here you see it's like a washer. So the area, no. So the volume in X is still like from a 0 to 1. So the volume it is 0 and 1 is pi is like f of x is like x squared. The g of x is minus x to the 4 dx. So this is the volume of these at the solid obtained a rotating region about the x-axis. Let's try like another example here. Set up the integral is about is like the volume of the solid obtained by rotating the region A about the horizontal line y equals to -5. Y equals -5. Since like a -5, it is under the g of x. Then this region can be expressed as it's going to be y equals -5 is a way under. So it's like this. Perhaps this is the y equals -5. Be 3 is more like 3 times 4. And this is like the region bounded by the washer. So this is like the radius is like, this is g of x, and this is f of x. This is the big washer. I'm gonna color this up. So this is like a big washer here. Gonna cover like the regions. The outer radius is inside gonna be gx minus 5, gx plus 5. Outer radius is fx minus -5 is x plus 5. So our out, it is x minus -5, it's going to be x plus 5. Inside radius, it is x squared minus -5, it is x squared plus 5. So I'm gonna color this region by like a more like effective way. Just gonna do them aggressively. So I want to save more time on it. So this is the washer. You can obtain by rotating the x on the 5 axis. And the volume, it is just gonna be 1 to like a 0 here. Our out are gonna be x plus 5 squared minus inner radius is x squared minus 5 x squared plus 5 squared. Dx. This is like the volume of this like washer. And we want to do another like shell method. If we have a region, example 2, is like, it's just like a region B is bounded by y equal to 2x to the square, and the vertical line is y equal to 54. And the y-axis, so part A, it is set up the integral area of region B. So it drives like y equal 54, so x equal to 3. So if it's at 54 equal to x equal to 3, then we get things like x is 2 times 27 and x equal to 3. So here's like the region. It's like y equals to 54. And this is like the region R is b equals to 3, x equal to 0 here. So 54 is about y equal to 3. So the area is going to be 3, 0, 54 minus a 2x to the cubic dx. So what if we want to like give volume of the solid, just rotating the region by the y-axis? So part B is like the volume of the solid obtained by rotating the region B just about the y-axis. Visualize this region. Just to draw like graph here. It might not to scale, but I just want to do like, if we have a graph, just do some visualize. Just do like dollar 3/4, rotating by the y-axis just is this. This like, this is like this is like the wall. This is just like the shell we want to produce. This is like the region. This is the shell we want to see. So it just is 2 pi x fx area s dx. So the volume at just 3 and then like 0 is 2 pi x. That's going to be 54 minus 2x to the cubic dx. So what about if it's rotating about the vertical line y equals to -2? So proceed as how about the x equal to -2 axis. So since x equal to -2, it is smaller than a. So this region is going to be like this. So we have, this is the y-axis is here. Oh, wow. This is like the axis. It's gonna be perhaps this is going to be the x to the -2 axis with the -2 rotating them. And this is like the area function just the other side of the. So this is like the shell here. So if you just draw the shell, you can just obtain this is the shell we want to. If you want to obtain, this is like the cross-sectional area. This is the shell we want. Just across the large region above. This is x -2. It's like x minus -2 is just x plus 2. As we obtain, this is going to be case 1, right? Case 2 in this region, so we set up the volume, it is 3 and a 0. It's going to be 2 pi x minus -2 x plus 2. 54 minus 2x to the cubic dx. So that's all for kind of a volume, just to how this set up like integrals. And I think that's all for today. Thank you for listening and have a good day. Yes, what area I'm really excited about.